Okay, hello everyone, I'm Longfei and I will talk about LiDO-DAG, which is our approach for formally verifying safety and liveness of DAG-based consensus protocols. So for the introduction, let's begin from the concept of consensus protocols. Well, in several blockchains, you have several clients submitting requests to a central distributed ledger. And the goal of consensus protocol is to make all the computing nodes in this system agree on a total order of these client requests. So for example, you have 3 replicas here, and they can all receive requests from clients. And the system can add these requests to the consensus log at an arbitrary order, but every replica must receive these requests in the same order. Now, given that consensus protocols play a central role in many distributed systems, including blockchains, you can easily think that there's a long line of work trying to optimize all different aspects of consensus protocols. So in 2019, the state-of-the-art of consensus protocol is probably hot stuff, which is still a Paxos-like leader-based consensus. But then in 2021, Liveness et al. Introduced the Narwhal protocol, which introduced the idea of having a DAG-based mempool in the consensus protocol. And subsequently, there is a very long line of work trying to optimize all different the throughput and latency properties of Narwhal. And furthermore, there is a general trend in the blockchain community to move away from leader-based consensus protocols and into these so-called DAG-based protocols. And this leads us to the central topic of this talk, which is DAG-based consensus. Here, DAG stands for Directed Acyclic Graph. These protocols all revolve around the following idea. We make the processes collaborate to build a DAG mempool of these data blocks or request blocks. And then we make these individual processes run an algorithm to interpret the locally observed DAG to get the consensus log. That's quite different from the Paxos-like leader-based consensus protocols. The advantage of these protocols is that you can get much better throughput than Paxos-like protocols. But with these additional components of mempool, you can imagine they have much more complex implementations and also much more complex security proofs. And like anything that gets too complex, inevitably we will have a lot of subtle bugs creeping into these protocols. So there has been multiple works which claim they found issues in previous proposed protocols, like this paper which says there is an issue with mysticity liveness proof, and this paper which says there are several robustness issues across DAG protocol implementations. Naturally, we want to ask, how can we give strong security guarantees to these protocols? Well, the only way to give absolute correctness guarantee to these protocols is to formally model them in a specification language and also construct mechanized proofs for these properties. But although you probably haven't heard of any of these protocols before this talk, you probably have heard of Paxos. And Paxos only relies on timers, and they don't have byzantine faults. And it's already difficult to verify Paxos. Now, DAG-based protocols use a lot more different components, and they have different states, such as timers, reliable broadcast, and other optimizations. So it's probably not a good idea to directly try to model every piece of detail of these protocols. So we ask, how can we abstractly specify the formal correctness criteria for these new protocols? How can we efficiently verify these protocols for the new of these properties for the new protocols? And how to make these proofs more reusable? Well, we claim we can handle all 3 challenges by introducing an abstract model for DAG-based consensus. And we can easily connect the different protocols in the literature to our model by refinement proofs. So for the rest of the talk, I will first give a bit more background about our work, and then we dive into the details of these protocols and how we formally verify them. So DAG-based protocols belong to a broader class of Byzantine fault tolerance protocols. So in any distributed system, we must prepare for a subset of the components to fail. And by Byzantine fault, we mean after a computing node fails, we assume it is corrupted and can inject any message into the system. And remember that the network infrastructure can also fail. And so we also need to assume the communication model. In this work, we mostly focus on the partially synchronous model, which says there is an unknown time point called the GST. And before GST, the network can arbitrarily drop or delay message delivery. But after GST, the network must deliver all messages within a known time bound. Let's call it delta. Now, there's a large number of consensus algorithms proposed for the partially synchronous Byzantine model, but most of them fall under what we call leader-based consensus. The basic idea is that at any given time, there is a single elected leader, and only this leader is proposing blocks to be committed by the other nodes. So you can see on the left, there is only this node 2 sending out those requests. But when this leader fails, we trigger a timeout or a view change protocol to make them switch the leader. Now, these protocols are easy to implement, and they are very well understood, but there's an obvious problem, which is that the leader is a bottleneck of network throughput. So people ask, can we make all processes make some progress even when they are not leaders? And the DAG-based protocol is essentially the current response to this question. The idea is that we have this DAG-based mempool. Each vertex on this graph represents a data block, and every process can add blocks to the mempool. And now from this figure, you can immediately see one thing, which is that this DAG graph only provides a partial order over these blocks. So it doesn't really give you a total order over the requests. And so we need an additional mechanism to reach consensus on the order. Now, exactly how this is achieved is now an active research area with many proposed solutions. We already saw in previous slides some of the major steps in this area, but there's many, many more protocols that are very recently proposed, and they are some of them are already deployed into existing blockchains. Now, why do we claim that we can use abstract models to simplify verification of these protocols? Well, abstract models give you a simple way to specify the expected behavior of a system. The idea is that you don't introduce all the network level details like timers and reliable broadcast all at once. You first specify a simple transition system which captures the core logic of these protocols. And then you gradually add in the network level details by refinement proof. And it turns out both safety and liveness can be proved by refinement. We will talk about how to do this later. In our last year's work, we proposed the LiDO model, which is an abstract model for leader-based consensus, and we applied it to several state-of-the-art consensus protocols. For example, this is how we proved the Ji-Yong protocol by layered refinement. At the top level, we have this abstract model, and then in the second layer, we add in the proposer state. Third layer, we add in those voter and the timer state, and finally, we reach the network state. So can we apply similar techniques to DAG-based consensus? And our answer is yes, which leads us to the core contribution of this work, which is the LiDO-DAG model. Now, before I introduce the technical details, it's useful to first have a rough idea of how these DAG-based protocols work. They usually work through three major steps. The first step is to designate a subset of the DAG vertices as so-called anchors or leader vertices. And how this is designated is protocol dependent. For example, this is a figure for the Bolshak protocol, which is a simple DAG-based protocol. And you can see that in every second round, you have one of the vertices marked red. And this is what we call the anchor vertices. It's essentially the anchor created by the leader of the odd number round. At any given moment, the individual processes observe a subgraph of the global DAG, and then the protocol defines an algorithm to interpret the locally observed DAG to get a list of the so-called committed anchors. And this is a total ordered list. And then we expand each anchor into the list of all directly or indirectly referenced blocks. So this means if your block is referenced by one of the anchors and this anchor gets committed, then your block also gets committed. And this is why with each commit of the protocol, we can commit a large number of data requests. Now, our key observation of this work is that these DAG-based protocols, although they seem quite different from leader-based consensus, we can actually interpret them as simulating leader-based consensus. Now, notice that in the previous figure I showed, there is only one anchor. Periodically, you have a single anchor in the graph. This actually, we can make an analogy between these anchors and leader proposals. Now, references to these anchors would correspond to commit votes. And recall that in Paxos-like protocols, you need a quorum of commit votes to commit a certain request. And so if we continue this analogy, then a quorum of references would correspond to a commit certificate. So can we formally capture this simulation? Well, we claim it's very easy to do so using our LiDO model. So here's a review of the LiDO model, which we proposed last year. It's an abstract transition system whose state consists of two major components. The first one is a cache tree representation of the consensus log. The second one is what we call the abstract pacemaker. The idea of the cache tree is that in leader-based consensus protocols, we can divide the system execution into views. And in each view, we postulate that the system has to progress through three abstract events, which we call pull, invoke, and push. Intuitively, what you do in each view is to append a single entry to the consensus log. But before you can append the entry, you have to first determine where to append your entry. And that's the pull step. And in invoke step, you actually append your entry. And in push step, you attempt to commit your entry, which might succeed or fail. And the cache tree is a graphical representation of the result of these steps. Here's an example. So you can see here that since Ccache represents a successful commit, and we don't have Ccache in the second view too, shown on the top right here, it's perfectly fine for the third view not to follow the second view and simply append from the method of the first view. You don't have to understand this because later I'll give a step-by-step demonstration for DAG-based protocol. Now, the cache tree representation is useful for proving safety of these protocols, but it's not sufficient to prove liveness, because to prove liveness, you have to show that after a leader sends out a request, the voters will vote for it before timeout. And this before timeout part is crucial. So we introduced the abstract pacemaker, which summarizes the state of local timers. So we know that when exactly these timers will time out. Now, the idea of LiDO-DAG model is as follows. In the DAG-based protocols, we still have this view succession, but these are logical views. These protocols don't explicitly introduce the idea of views, so they are logical. And in each logical view, there's still a pre-designated leader. And what it does is, instead of proposing a single block, it chooses one of the vertices in the global DAG as the new anchor to be committed. And so instead of having M caches or your invoke step proposing single block, you propose references to the DAG graph. So here's how the Bolshak protocol can be interpreted under this framework. Well, in the first round, you have this anchor A1. Naturally, it's attached to root because there's nothing before it. In the second round, this is we try to commit the A1 anchor, but it's not successful. You can see there's only one reference to it, and we need a quorum, which is 2 references. So in the second round, the second logical view, which is round 3, we have this anchor A2. Now, A2 doesn't reference A1, so A2 is also attached directly to root. In A3, we finally have an anchor that's committed. You can see that there are 2 references to it, which forms a quorum, and we represent it by a C cache over here. So if from this figure, we can see that the committed leader entry should be A2 and A3. And that's, in fact, exactly how the network level specification of Bolshak works. We also prove liveness of these protocols. It turns out that we can decompose liveness of them into the following safety conditions. First, of course, you have to periodically create new vertices, and then you have to make the leader vertices reference these vertices. And finally, we need to get them eventually committed. So we did several implementations of LiDO-DAG. Besides Bolshak, we also implemented Narble, which uses an external BFT to order these vertices. We also did selfish, and in fact, we did 2 versions of it. The second version optimizes the first one by removing 1 extra delta during failover. Our specifications are completely executable. We extracted them to OCaml. And here's the total proof effort. You can see it's a very lightweight way to verify these protocols. So what's the takeaway message of our work? Well, we showed that DAG-based consensus protocols can be interpreted as simulating leader-based consensus. And although it's a folklore that there's a strong analogy between these 2 kinds of protocols, we are the first to formally show that this simulation can be modeled as a refinement relation. And it turns out it's very easy to verify these protocols by proving this refinement. And that concludes my talk. For more technical details, please check out our technical report and artifacts. That's all. Thank you.
Any questions from the audience? Okay, I have a question. So within this framework of yours, can you reason about relative efficiency or optimality of these different protocols? I mean, presumably they're developing them because they care about making them as efficient as possible.
Yeah, so to prove liveness, of course, what we do at a network, what we do is we look at how the system state progresses through these each delta. So we say if the system at GST satisfies a certain condition, then at GST plus delta, you have to satisfy some additional conditions. So you can prove, say, since the protocol claims say we have a commit latency, say it's optimal 3 delta or something, then you can say at GST plus delta, if a leader proposes something at GST plus 4 delta, you will see it committed. And so you can verify all those latency claims in these protocols.